Why not? All right, motional EMF. The idea is in the words. What's an EMF? We haven't talked about one of those in a while. Evan, what do we got?
Electromotive force.
Electromotive force. What are the units on electromotive force? They aren't. They are volts. It is a misnamed thing. It is a potential difference supplying a current. It is not a force. The name comes from the fact that electricity is confusing, and so we didn't really know what was going on for a while when we were observing these effects. So it looked kind of force-like, but it's not measured in newtons. It is a potential difference that moves current around. What does motional mean? Related to moving. So the idea here is we are going to create a potential difference, a voltage, through motion. That's the idea. And we're going to set up a sort of made-up example to help us think through the concept. So it's something that's simplified to help us think through what's going on, but isn't very realistic. And then I've got some equipment over here so we can then look at the actual thing. We're going to start with a metal bar. That's our metal bar. This is the top-down view of said metal bar. There is copper wire that goes through the metal bar. So there are holes in the bar that allow that copper to go through, and the bar can slide along the rails. Maybe imagine taking a wire coat hanger, bending it into that sort of square U shape, and then putting a metal bar through the two wires that can slide up and down or left and right on it. Got the visual of what's going on here? Okay. We're going to put this thing in a magnetic field. Hold on. Let me think of the direction I want the magnetic field to be. I want it to be into the page, I think. If not, it's not the end of the world.
Should we use lots of colors?
It's up to you. I'm going to use lots of colors. I think it'll make the picture look a bit nicer. There's our magnetic field. So in this situation, I have a north pole sitting on top of the piece of paper, and I have a south pole sitting below the piece of paper, so that we can have this uniform field going into the page. I'm not going to draw the hand because the picture will get too messy, but I want you to imagine literally grabbing this bar, yanking it to the right. I'll draw an arrow indicating that force. We'll even write the words external force. Which could literally just be you grabbing and yanking the bar. And the whole bar is going to move to the right then with some velocity v. Resistive forces due to the magnetic field will allow the constant velocity to happen here. I want us to now imagine a fictional positive charge that lives in that bar. There's a lot of them. With the typical caveat of really it's electrons that are moving in the opposite direction, but we can't measure the difference, so we'll just pretend it's positive charges because that's the convention. And that's our system. The system right now is that guy right there. I'd like to draw the forces exerted on that charge. What forces are on that charge? There's magnetic forces. Magnetic forces. Moving magnetic field. Turn and talk to your neighbor. In which direction does it feel a magnetic force? Force. All right. Who's got the direction of the force for me? Which way is it going? Ooh, this is another time to give you a warning. Up and down are not as helpful of direction words, because up could mean toward the top of the page or out of the page. What do we mean here? Top of the page. It is indeed feeling a magnetic force in that direction.
Is it FM or FB?
FM is what we typically use. If you used FB, everyone would know what you're talking about, so that is perfectly fine as well.
Okay.
But M is the typical thing that's used. Let's get some subscripts going here. That's the magnetic force on the positive charge. I'm going to put B for this one. B for the magnetic field. Cool. That's going to cause the positive charge to do what? There are some side-to-side forces as this thing jostles back and forth, but we'll assume that the bar is thin enough that like those kind of cancel out, and we're just going to worry about the vertical stuff. It's going to go up. That's going to happen to a lot of positive charges. What's that going to leave at the top of the bar over time? A bunch of positive charges. Because all those positive charges will accelerate toward the top of the bar due to the magnetic force. Well, we're going to say they're confined to this bar right now. Eventually going to play, but enough of them are confined to the bar that they just kind of get flown up and then hit the walls side to side as they go up. Cool. If we have a bunch of positive charges going up, what's that going to leave behind at the bottom of the bar? Negative. It's going to leave behind a lack of positive charges. Because all of them, not all of them, a lot of them have moved toward the top of the bar. Got a bunch of plus at the top, a bunch of minus on the bottom. That makes our metal bar look kind of like what?
Polarized?
It is polarized for sure. That is exactly what it is, which then makes it act like what circuit element?
A battery.
And it's kind of battery-like, isn't it? It's got some positive. It's got a positive end and a negative end. It's got an electric field in it now because there is a charge separation, because it is polarized. So we've created something that acts like a battery without needing battery acid or lithium ions or chemicals to make that happen. It's just a piece of metal moving in a magnetic field. So that's pretty neat. Because of this charge distribution, there's now an electric field in the wire pointed in which direction? Toward the bottom of the page from positive to negative, which means that this positive, the next positive charge, after a bunch of them have moved up, feels an electric force in which direction? Toward the bottom of the page. We also have an electric force on the positive charge by, we'll say, the electric field. This is something that's hard to draw in a picture out loud. Out loud is, as it starts to happen, there's a stronger force than negative electric force, which is what makes the particles move toward the bar. But over time, as the charge gets more and more, this electric force grows bigger and bigger and bigger. And that will occur until the two forces balance each other out. So So we'll get to a point. This is not instantaneous. It's pretty fast though. Where they balance each other out. Enough positive charge rated from the negative charges to make it balance the magnetic field. Why is it balanced? Well, if it's the magnetic force is strong, get more positive charges going up. If the stronger, we'll send some of them back down, and so it's kind of down. And so it's kind of this sort of balance until they've reached an equilibrium. Yes.
Does that mean that
Yes, it does mean that. Yeah, because we're in a uniform magnetic field. Yeah. So charges will distribute themselves across the cell bar in such a way that happens. And again, it's an equilibrium, not a balance over, and then over time they'll balance each other. So this is true. This is one. We have equilibrium is what I'll call it. There's no official term for that. Balance force, no motion. It just means constant velocity. So the positive charges will keep flowing in that bar as we pull to the right, and we're connected to other pieces of copper. They can go this way and this way and this way and this way and keep looping. And so we've generated current through current closed loop just by pulling. So we get now current that from the positive end of our fake battery to the negative end of our fake battery. How much depends on the resistance of, in this situation, or in any situation, the resistance of connected. So the last thing we're going to do is come up with an expression for the voltage, the potential, the EMF, the electromotive force that's generated here. This is the concept behind that mathematics we're about to do though. Now's a great time for questions. Evan.
Does the external force how it's reaching that movement equilibrium, or does that be exerted?
It needs to be continued to exert because magnetic resist that change. So there's a magnet resisting that change. It does need to be continuously applied. If not, we would get power from nothing, which would be pretty cool. Yeah.
To me, this is like use real life, right?
For sure. Not this toy example, but this concept definitely is.
What like is like how that external force? What is used?
Sure. So this in a very broad sense is doing to provide electricity to us right now. So what mostly to provide that force is burn some coal, build some water. Water generates steam. That's the turbine, and that turbine is what this. So that's typically done. In a nuclear plant is the exact same problem. Burning coal, you have nuclear fission going on. A windmill, wind that's turning that turbine, and that's what's exerting the force. So most of energy production works hands of how do we generate that force in a way cheap and clean and efficient, cause climate change, or at least reduces how bad the impact on the environment is. Those sorts of things. Art.
Yeah, I thought it's like the movement
It's very.
So then how can you have
Yes. Yeah, so that's where it's not. There is a transient part of builds up, but it happens.
magnetic force?
Yes, right. Yeah. This magnetic force is, and then as the charges move up, this grows bigger and bigger over time until that you reached. Yeah, and the amount of time over which that happens is, I don't actually know the order of magnitude, but like in microseconds, something like that, something very rapid. Yes.
Why is that further up?
Because there was SAT testing happening in here yesterday. Last year, I had a poster that's still not put back up that they made me take down of the standard model of physics, which talks about that aren't that, and they made me take that down. It's not going to help any CT. Quarks and bosons are not a thing. Anyways, I don't also think the table helps on the SAT, but put it up for some reason. All right.
Maybe we could have like a secret message.
That's fun.
How does the current last? Like, what did you imagine that it just eventually go away?
Because you keep pulling on the bar.
Yeah, but like, how does the equilibrium eventually achieve equilibrium?
Equal constant velocity flow, not. Yes, the equilibrium isn't no flow. It's that the flow is at a constant rate. Charlie.
How do they keep like pulling on the bar? Like, is it infinite?
In this situation, we don't run out of wire here. Yeah, that wire goes on. As long as we need to. So what we would do if we want to do this in practice is instead of pulling in one direction, oscillate back and forth, which would instead of flowing in one direction, the electrons would just kind of slosh back and forth, and that sloshing back and forth is enough to power devices. What power companies do. Like the outlets here are 140 volts, but that's not electrons flowing in one direction. That's just them going back and forth. So you, in practice, would kind of oscillate this rather than pull it in one direction for that reason, because you run out of room otherwise. Yes.
With a wind turbine,
Uh-huh.
how do you make it just start going back and forth?
So with any sort of turbine, the rotation takes care of that. Takes care of every 180 degrees the coil is flipped relative to the magnetic field. So that happens automatically anytime you're turning stuff. Yeah.
If they're sloshing back and forth, how do they ever like leave to start powering stuff instead of?
They don't. The electrons at Ameren, company in St. Louis. I keep saying that, but you all don't pay power bills, so you may or may not know. Ameren, the electrons at Ameren do not get to us. They send an electric field down the wires, which then moves the electrons that are already here in our wires. So it's really power companies are sending electric fields from them to us to move the electrons that are already present in our wires. Yeah, we don't get electrons from them. We get electric fields from them. Which is pretty wild. Because electrons are also sloshing like very slow. Like it's centimeters per second. And so they're not getting anywhere fast. Great questions. Other questions? Yes, Sophia.
They're like sloshing back slow. How does something like that work? Because don't you need it to be moving fast?
No, you don't need it fast.
Okay.
You just need it moving.
Okay.
Yeah. Yeah, while we're on the topic, I guess we'll get the visual of this from the FET simulation. Then we'll come back. FET circuits. This says DC, but I need AC. This one. So this is what alternating current is, which we don't study much in AP Physics 2, but I do think it's important that you're aware that it exists. That symbol is Ameren. This light bulb is, I guess, Clayton High School. That is everything we are powering here at Clayton High School. So the electrons literally just look like that. Can I zoom in? Just a little back and forth of the electrons. I don't think the light bulbs do it here very much. The last school I taught at was very true. If you record something in slow motion, you can actually see that flicker of the light bulbs. These light bulbs are flickering like that at 60 hertz, 60 times per second. And it's actually 120 flashes per second because it's the top and then bottom of a sine wave. And so that's faster than, for lack of a better term, the refresh rate of our eyes. Like our eyes cannot discern that that's happening, but it is. Like these lights are flashing right now, 120 times per second, which is pretty wild.
Are they all flashing at once?
Together, yeah, because they're all connected in parallel to the same power supply. Yeah,
That's really weird.
it is really weird. I'm gonna take a slow motion video real quick. I don't think that
And it's just like
it has room. All right, do we see the lights flashing in this room? No, we don't. So some counter that to have a coating on them that stay glowing even when there's not power, prevents the flashing effect from occurring for these light bulbs. But yeah, pretty crazy. Yeah.
So if it's just like cycling the same electrons over and over,
Mhm.
how does anything like ever run out of battery?
So batteries are different than this process. So this process would end if Ameren stopped burning coal. Like that would be the source of fuel at the other end is gone. For a battery, it's the chemical potential difference due to the battery acid that eventually is unable to continue moving electrons and sustain an electric field.
Maybe I phrased that wrong. Like,
Yeah.
How do like light bulbs ever burn out?
Oh, sure.
As opposed to like lasting forever.
Sure. So the way that a traditional light bulb works is that the light is just, it's glowing, it's getting so hot that it glows in the visible spectrum. And that's just due to friction of the electrons. And so it gets so hot that this wear and tear over time that it melts, essentially. And then an LED light bulb lasts much longer because that's not how it generates light. But again, just over time, the wear and tear is what does it. That's why LEDs are so much more efficient and last so much longer, is because that's not the process by which they generate light.
Don't they do that on purpose, though?
Don't they do what on purpose? Do what on purpose?
Like, make light burn?
So,
And then you continue.
so there is a theory out there, and there's some truth to it, that 100 years ago, a sort of conspiracy theory of the light bulb companies all got together and said we could make light bulbs that last forever, but then we won't make money, so let's make them that last a couple months. Which is sort of true, but also the light bulbs that generate are really dim and kind of suck. So, but also you get better light with the light bulbs that don't last as long. So it's not all conspiracy theory. Yeah.
I just want to make sure I understand. It's like the
Sure.
circuits that we like made in class, they don't do this.
They don't. If we disconnect
Okay.
Ameren here, how do I disconnect?
Battery.
And instead,
Okay.
you get what's called direct current, and they keep going in one loop.
Okay, but this is not how the light bulbs up here
Right.
work.
Yep.
Okay.
Because they are generated through, or the electric field which moves the electrons is generated through this process. And so we'll talk more about how that works today and tomorrow. But it's a different process than a battery. It's this motional EMF sort of process. Other questions? All right, so let's finish up this now. Wait, why is full screen not working? Anyways, I don't know. This doesn't want to go full screen anymore. Oh well. Okay. Work. Last thing we talk about then is for the given speed this thing is moving, how much of a voltage are we generating? So that's going to come from this force diagram. We are going to, just for fun, let's do the full problem-solving approach with this. The net force in the y direction, the net force in the y direction when we add up our forces is the magnetic force on the particle by the magnetic field plus the electric force on the particle by the electric field. We'll choose up to be our positive y direction, so that when we write scalar equations, the net force in the y direction is 0. Net force in the y direction is a positive magnetic force and a negative electric force based on those directions. So 0 is equal to that positive magnetic force minus that electric force, or the electric force equals the magnetic force. Do you still have to do every step there? No. You could have gone right to here, I'd be happy. Yeah. We've graduated past that.
I have a question. Are the kids at your new school going to have to do all this?
Yeah, of course.
The full problem solving?
Yeah. I'm not going to change that I think it's useful. So here's the thing, is you definitely graduate past the need to do all of this. Like, it's not something that's needed forever. But when you're first learning why are things positive, why are things negative, what does it mean to add up forces? It means I can tell you about the motion, but I can also tell you about the force diagram. Those two things are related. It's helpful to have a structure to help you think through all of those things. Once you know to think through all of those things, you don't need to write it all out anymore. So it is a teaching tool, not something that's necessary forever. The freshmen are also pretty much the Miliano, really. And the answer is no, they don't really need to anymore. They've got it. Anyways, electric forces. How do you compute those? How do you compute a math model for that? QE. V would be the energy. QE is the force. Magnetic forces. How do we do those? That's our new one. QVB. Q's cancel. That's nice. What are we looking for? We are looking for potential difference. Reminder that the electric field is the steepness of the potential hill and so what that means for us is E equals delta V over, I'm going to call the length of this bar, my picture's almost perfect. We're out of room for that. I'll put it here. That length we're going to call, I think cursive L is the variable used in the AP Physics 2 equation sheet. I'll be consistent. What's that? Yeah, from one end of the copper wire to the other, or the length. Yeah, the length across which the bar is in the field. These lowercase l, they do. Okay. So backing up now to here, E equals delta V over L. So I can replace this E with delta V over L. Or the potential difference, which is what we want, is V times B times L. On the left there is a capital V, on the right is a lowercase v. When we're talking about EMFs, when we're talking about potential difference as an electromotive force, what's the variable that's often used instead of delta V? Swirly E, epsilon. And that's how you see it on the equation sheet. Hopefully this makes some sense if we think about this equation. You get a stronger potential difference, the bar is going faster, if it's in a stronger magnetic field, and if it's longer so that there are more charges in that field moving. And then you often use this when problem solving in conjunction with potential difference equals current times resistance, V equals IR, this being the V in that case, to figure out how much current is flowing or something like that. A little side note, use with epsilon equals current times resistance when problem solving. Why what?
Why is it a different symbol?
Why is it a different symbol? That's a great question. And the main answer is that this potential difference in general can't be localized is the word we use. We can't say that here is the higher potential, here is the lower potential. We kind of can in the picture I drew. But for the most part, it's kind of, because it's a magnetic force that's actually moving the charges instead of an electric field, we can't say here's the higher part of the potential, here's the lower part of the potential. And so we use a different symbol because we are using a magnetic force to move charges in a way that looks like a voltage instead of actually being a voltage, which is kind of wild. Yeah, so it's hard to think about.
Wait, so is it the magnetic field that's creating the current, or is it the voltage that makes the current from the magnetic field?
Yes? It's a little bit of all of that? Yeah. Yeah, great question.
I'm just confused about why resistance would be in there at all.
So this wire has some resistance, or maybe you connect a resistor in your wire. So eventually you're going to hook this up to something you want to power, and that thing you want to power will have resistance.
And we're looking at the change of potential between what's on either side of the bar,
Yep,
like positive or negative side, or like left to right?
top to bottom. So from positive to negative. Yep. Yeah, Carter.
So if you know which side is positive and which side is negative, don't you know the direction of the voltage?
For this particular derivation, yes. It's not going to be true for all generalizations of this that we look at. There's positive and negative end for all of them.
But how? Can't you?
Because it'll be a magnetic force on the charges.
But like, can't you just like see? Okay, these are positive charges, these are negatives.
From a particular frame of reference, there won't be an electric field that's moving them. It's just a magnetic field that's moving them around. And that is the third most correct answer is that these conventions show that over time. When we first studied them, they looked different. The same thing. They're part of the answer. All right, question about derivation.